Imagine this, a single piece of steel that can hold the weight of 100 fully loaded semi-trucks. How? It's all about a shape engineers call the I-beam. This isn't just metal, it's the backbone of our cities, born from rusted scrap and forged in lightning, fire, and thousands of tons of pressure. But here's the kicker. Why are brand new I-beams almost entirely made of the past? Cars from the 70s, rails from the 30s, even armor from World War II. All of it could be holding up a modern skyscraper. Stick around and you'll learn a secret that will change the way you think about the power of steel. The genius of the I-beam is its shape. The real heavy lifting is carried by the top and bottom parts, so that's where most of the metal is packed, in the flanges. The thin web in the middle just keeps them locked in place. This gives you maximum strength for minimum weight. And that strength is just insane. A single heavy I-beam, set up right, can handle loads of hundreds of thousands, sometimes even millions of pounds. Picture a whole line of fully loaded semi-trucks, all parked on one single piece of steel. That's real power. This story doesn't start in some shiny workshop. It starts in a massive, rusty, noisy yard that looks like a graveyard for metal giants. This is a scrap yard. Mountains of old cars, chopped up rail cars, building frames, and industrial junk are all waiting for a second chance. A giant crane with a powerful electromagnet drops down on the pile, and with a metallic groan, tons of old iron leap up to meet it. This scrap is the main ingredient. It gets loaded into a huge steel basket and sent to the melt shop for its trial by fire. Steel is the undisputed champion of recycling. The recycling rate for structural steel in the US is a whopping 98%. That means nearly every piece of steel from torn down buildings, old bridges, and scrapped ships gets put back to work. On average, a new I-beam made today is 90% recycled metal. This creates an incredible, endless loop. A skyscraper going up today could have a piece of a 70s muscle car, a 1930s railroad track, and even armor from a World War II battleship inside it. This isn't just a hunk of steel. It's concentrated history, melted down and reborn for a new tour of duty. So these numbers aren't just stats. They're the silent language our cities are built on, a language of strength, efficiency, and the almost endless life of metal. Every year, the United States cranks out over 5 million tons of structural steel, and the lion's share of that is I-beams. That's a number so big, it's hard to get your head around. Let's try. The steel in the famous Golden Gate Bridge weighs about 83,000 tons. That means, in 1 year, American mills produce enough beams to build over 60 Golden Gate bridges. The heart of the plant is the electric arc furnace, a giant kettle, the size of a small house, where our scrap metal is dumped with a thunderous crash. 3 massive graphite electrodes, thick as ancient trees, are lowered in from the top. And then the operator hits the juice. An electric arc, basically a man-made lightning bolt, erupts between the electrode tips and the metal with incredible force. The shop fills with a deep, bone-rattling roar, and the light from the arc is blinding. The temperature inside instantly shoots up to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts to melt, turning into a boiling, blazing lake of steel. Special additives are tossed into this molten bath to get the exact grade of steel needed, strong but flexible enough to handle massive loads. When the steel is ready, it's time to turn this liquid river into something solid. The molten metal is poured into a continuous casting machine. The blazing liquid flows into a special, water-cooled copper mold. As it passes through, the outer layer of steel freezes, forming a thin skin. Next, this still mushy on the inside ingot is continuously pulled downwards through a chamber of water spray where hundreds of nozzles blast it, forcing it to solidify all the way through. What crawls out of the machine is an endless, glowing red, massive steel billet. This is called a bloom. Automated torches hiss to life and slice off pieces to the right length, say 20 or 30 feet. This is our blank, our piece of dough that we're about to shape into a beam. These hot but now solid blooms are sent to the next furnace, the reheating furnace. It's like a giant tunnel with a fire roaring inside. The blank moves slowly through it, where its temperature is cranked back up to the perfect working heat, around 2,200 degrees Fahrenheit. It becomes soft and pliable, like clay, ready for the most important step, rolling. And this is where the real show begins. The bloom, glowing a brilliant orange, rolls out of the furnace and hits the rolling mill. This is a series of giant steel rollers, like massive rolling pins, lined up one after another. But these rollers aren't flat. They have special grooves cut into them, shaped to gradually form an I-beam. The bloom slams into the first set of rollers. They squeeze it with thousands of tons of force, making it a little thinner and longer. Out the other side, it's grabbed by the next set, which squeezes it from a different angle, starting to form the flanges and the web of the future beam. And so, step by step, passing through dozens of these roller sets, our shapeless billet is stretched and molded, taking on that familiar I shape right before your eyes. It's an incredible sight. A piece of glowing steel that started at 20 feet long gets stretched into a fiery ribbon hundreds of feet long. The whole mill is filled with a symphony of bangs, screeches, and the hiss of water keeping the rollers cool. When the beam exits the final, finishing roller, it has the perfect shape and dimensions, down to a fraction of an inch. Hot, long, like a fire serpent, it travels down a roller conveyor to a massive cooling bed. This is a giant rack where the beam slowly cools, letting its heat radiate into the air. As it cools, the metal shrinks a bit, and sometimes the beam can get a slight warp. To fix that, after it's cooled down, it's sent to a straightener. This thing is like a giant steel chiropractor, passing the beam through a set of rollers that align it until it's perfectly straight. So, we have a perfectly straight, long beam, but it's not ready to ship yet. Time for the finishing touches. First, it's cut to the specific lengths the customer ordered. This is done by giant saws with blades 6 or 7 feet across. With a deafening scream and a shower of sparks, the saw cuts through the thick steel in seconds. Then, every single beam goes through a tough quality control check. Inspectors measure its geometry, and special ultrasonic machines scan the metal to make sure there are no hidden cracks or flaws inside. Only then does the beam get its marking, its birth certificate, with the steel grade, size, and batch number. The finished inspected beams are picked up by giant cranes and stacked in the yard, or loaded directly onto special railcars or trucks. And just like that, this steel backbone, born from rusty scrap, forged through fire and pressure, is ready to ship out to a job site, to become the silent but incredibly strong skeleton for a skyscraper that will scrape the clouds, or a bridge that will connect two shores. Standard beams on a construction site can be anywhere from a few inches to 3 feet tall. But then there are the real monsters, the so-called jumbo sections, used in the most critical spots of skyscrapers. Their height can be over 4 feet, and their weight is something else. The heaviest ones can weigh over 800 pounds per foot. Think about that. Every foot of that beam weighs as much as 3 grown men. And a standard length for these things is 60, 80, or even 120 feet. A single one of those beams can weigh as much as a battle tank. Then there are 2 paths, either long-term dry storage in double-walled concrete containers, or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Transportation is under guard on a special route with an escort, GPS, and mandatory 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor-grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark grey color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part, isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid. Basically, a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. Yellowcake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellowcake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellowcake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade, if you can find any. There are 2 ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video.